Hi, this is Alfozia Nihar from At Home Tuition. Welcome to our session today. The topic that we are going to discuss in our today's video is part 2 of our previous video, L'Hospital's rule and its indeterminate forms. In our previous video, we were looking at the rules that work great on the two indeterminate form 0 over 0 and plus or minus infinity over plus or minus infinity. There are more of the indeterminate forms out there as we saw earlier. I'm going to take few examples. We will start with the indeterminate form 0 plus or minus infinity. So this is the form of the indeterminate form. Let us evaluate an example and I'm going to show you step-by-step solution for that. Here is the example question. Please have a glance over this. Limit x tends to 0 from the positive side, x times ln x. Note that we really do need to do the right hand limit here. We know that the natural logarithm is only defined for positive x, and so this is the only limit that makes any sense. Now in the limit we get the indeterminate form 0, negative infinity. L'Hospital's rules won't work on products. It only works on quotients. However, we can turn this into a fraction if we rewrite things a little. Generally we know how to write a product as a quotient. You can just write this as a numerator divided by a fraction. You can just write it as 1 over x. It is just like taking the reciprocal. So let us rewrite this first. Hope you are clear with this step. This function is the same, but we have just rewritten it, and the limit is now of the form negative infinity over infinity. So we can now use the L'Hospital's rules because that rule is applicable only with the quotients. So I'm going to rewrite this as ln. I'm going to find the derivative of the numerator and derivative of the denominator because that is the rule for L'Hospital's rule. You can also refer our first video for more information of the introduction part. Okay, I'm going to do the differentiation. First derivative. Derivative of the numerator is 1 over x. Derivative of the denominator would become negative 1 over x square. Am I right? We can do fractional division here. Now this is a mess, but it cleans up nicely. I'm going to just apply this fractional division. 1 over x times x square over negative 1. Am I right? This is how we do the fractional division. We just change the sign in between the division into product and just multiply it by the reciprocal of the denominator. So by doing so, I'm getting negative x if I simplify. Hope you're getting the same value. Now just apply the limit. So you'll be getting a 0. Hope you're clear with this example. In this example, we use the fact that we can always write a product of functions as a quotient by doing one of the following. Let me state it as a formula. So a fraction, a product can be written as a quotient of this form, or you can also rewrite the same thing as in this way. It depends upon the question. If the question is difficult to rewrite in this form, you can use this format. So using these two facts will allow us to turn any limit of the form 0 of plus or minus infinity into a limit in the form 0 over 0 or plus or minus infinity over plus or minus infinity. Which one of these two we get after doing the rewrite will depend upon which fact we use to do to rewrite. So one of the rewrites will give 0 over 0 and the other will give. So these are the two indeterminate forms. It all depends on which function stays in the numerator and which gets moved down to the denominator. Hope you're clear with this concept. Okay, let's take a look at another example. Please look at this question. Evaluate the following limit. Limit x tends to negative infinity x times e raised to x. So it is in the form infinity times 0. We used to identify the indeterminate form just by plugging in the limit, the value of x in the function. So if I substitute this here, I'll get infinity times 0. So this means that we will need to write it as a quotient because a product cannot be, the problems with a product cannot be used in L'Hospital's rule. So moving the x to the denominator, I'm going to shift this to the denominator. You can also try the same question with shifting e of x, e raised to x to the denominator. Now I am going to shift x to the denominator. So let's try that with this problem as well, because we did the same thing in the previous problem. Same format. So I'm just going to rewrite. I'm not going to do any calculation right now. Writing the product in this way gives us a product that has a form 0 over 0 in the limit. So we are allowed to use L'Hospital's rules on the quotient. So by L'Hospital's rules means we are going to differentiate the numerator separately, denominator separately, and then we are going to apply the limit. So let's differentiate the numerator and the denominator. Again we end up with 0 over 0 indeterminate form, right? So let's try differentiating again. So by differentiating the top and the numerator and denominator, we get still 0 over 0 indeterminate form. Okay, let me do the differentiation again. We have to do the differentiation again and again until we get the form which can give you an answer except the indeterminate form. So let's try that. I'm going to differentiate the numerator and denominator separately again. Okay, I'm going to do some more trials. This doesn't seem to be getting us anywhere. With each application of L'Hospital's rule, we just end up with another 0 over 0 indeterminate form. Am I right? And in fact, the derivative seems to be getting worse and worse. Also note that if we simplify the quotient back into a product, we would just end up with either infinity times 0 or negative infinity times 0. Am I right? So that won't do us any good. So this does not mean, however, that the limit can't be done. It just means that we move the wrong function to the denominator. Does this make sense to you? Okay, let's move the exponential function instead and try the same thing. We are trying the second form. I have just shifted e raised to x to the denominator. You can also rewrite 1 over e raised to x as e raised to negative x. Am I right? So we are going to use that fact here. I have done this so that I can simplify the quotient up a little. So this will help us when it comes time to take some derivatives. The quotient is now in the indeterminate form of negative infinity over infinity. So we are going to use L'Hospital's rule. By using that, it will give us, so if I find the derivative of the numerator, that will turn into 1. And if I find the derivative of the denominator, I'll get negative e raised to minus x. So if I apply the limit there, I'll just get 0. This is the step where I found the derivative of numerator and denominator. Now I'm just going to apply the limit. So I'll get, that's it for this example. So you should know when to shift the first function to the denominator and when you should shift the second function to the denominator. So it purely depends upon the question. If you try the first format and if you're not getting the answer, please do not worry. It means you have shifted the wrong function to the denominator. So it means you have to shift the other function to the denominator and proceed with the steps. So when faced with a product of the type 0 plus or minus infinity, we can turn into a quotient that will allow us to use L'Hospital's rule. However, as we saw in the last example, we need to be careful with how we do that on occasion. Sometimes we can use either quotient and in other cases only one will work. Let us now take a look at the indeterminate forms. So these are the next set of indeterminate forms. These can all be dealt with in the following way. So we will just work one example. Here is the example question. Here is the example question. In the limit, this is of the indeterminate form. If I plug in infinity here, I'll get infinity raised to 0. So this is of this type. We are actually going to spend most of the problem on a different limit. So let's first define the following. Let this function be equal to a variable. Generally we used to assume this as y. Now if we take the natural log of both these sides, first let me assume y equal to, so whenever we want to shift the variable from the exponent's place to the base, we used to take the natural log. Am I right? I'm going to do the same thing here. Taking natural log of both these sides, we get ln of y equal to ln of x raised to 1 over x. By applying the rule, then exponent will be shifted to this place. So we will get 1 over x times ln of x. This can also be written as ln of x over x. Am I right? So this method will be helpful for us to rewrite the question of this form. So this can be written as limit x tends to infinity of y, where y is equal to ln of x over x. So you can replace this as ln of y, so that you can equate the function equal to ln of x over x. And then you can differentiate the numerator and denominator, because this is of the quotient type. Ln of y is nothing but ln of x over x. Applying the rule, I mean differentiating the numerator, I'll get 1 over x. Differentiating the denominator, I'll just get 1. If we apply the limit, we will get 0. This limit was just a L'Hospital's rule problem, and we know how to do those. So what did this have to do with our limit? Well, first notice that e raised to ln of y is equal to y. Am I right? So if this is possible, so our limit could be written as, you can just rewrite that as, I'm just going to show that step for you. This would be more apt when compared to the previous step. We can now use the limit above to finish this problem. So you need not do in this way. I'm just explaining you this, that this will turn into 0. Now let us complete the problem. So if you apply this, you'll get 0 here. So e raised to 0 is nothing but 1. With L'Hospital's rule, we are now able to take the limit of a wide variety of indeterminate forms. Am I right? That we are unable to deal with prior to this video. Hope you are clear with all the examples. Now you can able to do all the problems on the wide variety of indeterminate forms. In case if you get any question regarding this topic, you can let me know. See you in the next video. Have a great time.